Hello and a good time of day to you. Inside this box should be another ZX Spectrum that has been sent to me for repair. I believe the case has been sent just to offer protection for the circuit board inside, and I'm not expected to do anything to the case. So let's have a look inside. I've already seen some photographs of the circuit board, so I know what should be in here, and I know that it's also suffered a rather messy attempt at repair by someone else, though I think not its present owner. Here it is. I can see that it's had a reset button fitted, which I suppose is a useful addition. I'm going to have to unscrew that in order to free it from the upper part of the case. And we can see here that this transistor TR4 has been horribly replaced with this thing on a set of flying leads. That's clearly no good at all. That'll have to be removed. Here's a closer look at the circuit board. Not only has transistor TR4 been replaced by this one on a flying lead, but it looks as if the original circuit board pads down in here have been destroyed, so fitting a replacement is probably going to be rather difficult, but I'm sure it'll be possible to fit one in somewhere. The transistor next to it, TR5, is clearly not the original one either, though perhaps I'll retain it if it's an appropriate replacement and in working order. This circuit board has the later version of the voltage converter circuit installed on it, although on a board designed for the earlier version. Many of them were assembled like this in the factory, so I expect this one was too. And for example, we can tell because some of the components are in places where it seems they shouldn't be. This capacitor up here, for example, and the way these diodes are connected. I've also removed the heatsink from the voltage regulator to make it easier to work on the circuit board, although that proved to be much more difficult than usual. It was as if the nut on the rear of the board had somehow been welded to the bolt, and the top of the bolt welded to the flange of the heatsink. I absolutely could not undo the nut at all, so I had to resort to using a drill to remove the head of the bolt. I will very quickly make some resistance measurements across some of the power supply lines and at the voltage converter's inductor coil. If you want to know more about these tests, then have a look at the video about initial tests to make on a Spectrum. However, I won't pay much attention to the results I get at this point. Once I've done that, I'll remove transistors TR4 and TR5 and replace all of the electrolytic capacitors. Perhaps slightly surprisingly, all those tests gave results roughly within the expected ranges. I've replaced all the electrolytic capacitors apart from C74, which I've removed from this location here but not replaced yet, because I first need to work out how to replace transistor TR4 here, and it'll probably be easier to do that without the capacitor in the way. If you look closely, you can see that two of the circuit board pads for transistor TR4, the lower two down here, have been destroyed. They're missing from the underside as well. However, this one is still intact. Someone has installed these two little wires from nearby locations to connect the previous transistor that was installed there. So first of all, I'm going to check to see whether they are connected to the correct places, and then I need to decide whether I want to use those or install the transistor somewhere else. And given that both of these come from places very nearby, I think it might be easier, if they're correct, to remove them and then just insert the new transistor's legs into the holes where those little leads come from. So here's a part of the circuit diagram of the voltage converter circuit. Now there are several different variations of this, and as I mentioned earlier, I think this Spectrum has the later version, and so it may not be exactly the same as the one shown in this diagram. But that doesn't matter, because the transistors are connected in the same way in all of them. And we'll start off by having a look at transistor TR4, which is this one here. I've got a multimeter set up in its conductivity test mode, so you'll hear it beep, and then there's a low resistance between its probes. Now I know that normally the middle pin of transistor TR4 is its base, and if we look at this diagram, TR4's base connects to one side of one of the inductor windings. So if I place this probe here on this lead that has gone to the middle terminal of that transistor and try either side of the inductor, there's connectivity there. So that's probably correct. This lower connection here, well, that must be either its emitter or its collector. Now its collector goes to the other side of the inductor, to the other inductor winding. So if I pull one probe there and try the other inductor winding, yes, it beeps. So that must be TR4's collector, and its emitter goes to the 0 volt line, which is the pad that's still intact. So we'll check that. So these two little leads here do go to the correct place. I just need to decide whether I'm going to use those to install transistor TR4. Let me just remind myself of how TR5 is connected as well. The pads for that seem to be undamaged. Again, I know that transistor has its base terminal in the middle, and here its base terminal goes to the more negative side of capacitor C74, which is the one I've not installed. So that's correct, the center terminal is the base. I elected to remove the short wires that were there previously and have installed a new ZTX653 transistor for TR4, bending its legs into these slightly unusual positions so it could reach the appropriate connection points. I want to make some continuity checks again to make sure it is connected properly. So this lead on the right handmost side is the transistor's emitter, and that should be connected to the 0 volt line, which it is. Next round the middle lead is its base, and that should be connected to one side or the one coil winding or the other of the inductor coils. That one, yes, it is. And then the remaining leg, this one over here, is its collector and should be connected to the other inductor winding. It is, so that's good. I think that should work properly. So now I'm going to install a new transistor for TR5. I use a BC557, which I know is an appropriate replacement. Like the original, its middle lead is its base. However, the collector and emitter are reversed compared to the original, so I need to install it facing the other way around from that indicated by the silkscreen marking. I'll also install the replacement 4.7 microfarad capacitor for C74. Those two components replaced, I've just removed the 7805 voltage regulator. I don't know whether it's good, but I quite badly damaged its metal tab, so I'm going to replace it with this new one. Unfortunately, the alignment of the terminal holes and the mounting hole for the bolt that holds the heatsink in place is not quite right on most spectrums and requires the leads of the voltage regulator to be bent into a slightly strange position. Something like that is usually right. Let's see whether it fits. When soldering the regulator in place, it's important to do it with the heatsink and its bolt installed, so it'll be in its correct final position, and the connections, the joints, won't be stressed unduly when the heatsink is installed later. I've cleaned down the workbench and the circuit board to get rid of any stray solder blobs, etc. So I think it's now time to try turning this on. I was expecting the internals of the RF modulator to be missing, because the owner had told me about that, but the composite video signal is connected by this little wire here straight through to the output connector, which I've plugged into a television's composite video input. I've got this multimeter here ready to measure some voltages if appropriate, and this oscilloscope probe is connected to the collector of transistor TR5, so I'll be able to see straight away whether or not the voltage converter circuit is oscillating as it should. The power input is ready for me to connect to a bench power supply, which will feed it 9 volts with a limit of just over 700 milliamps. So here we go, let's see what happens. And I've switched the power off again. The current limit on the power supply activated and remained so, and I could see on the oscilloscope that the voltage converter circuit wasn't oscillating, so that's very disappointing. There's still something wrong. This illustrates the enormous advantage of using a bench power supply with a current limiting feature. Without that, transistor TR4 would almost certainly have been destroyed just now. However, I don't expect it has. It would be very useful to know whether the cause of the problem we've just seen was an overload on the 5-volt power supply line, in which case it could be due to a fault in any of the ICs in this spectrum or a number of other components, or whether it was due to one of the output supply rails, the -5-volt or 12-volt lines generated by the voltage converter circuit, the diagram of which you can see here. Now, I noted that when the power was switched on the oscilloscope I could see that the collector of transistor TR5, this point here, was sitting at a steady voltage of just below 2 volts, which is very similar to the voltage that was on the 5-volt supply line at the time, and I measured later while the camera wasn't running. This suggests that transistor TR5 was switched on, and this happens when the 12-volt output of this circuit is too low. The base of TR5 is connected to this point here, and it samples a portion of the 12-volt output due to the divider action of these two resistors. If the output is too low, TR5 turns on and allows energy to build up in the primary winding of this inductor. The problem is, if something prevents the output from ever reaching the desired value, then TR5 turns on permanently, causing transistor TR4 to do the same, which forms a short circuit between the 5-volt power supply line, through the secondary winding of the inductor, through TR4 and to 0 volts. If there's nothing to limit the current that flows in that situation, then TR4 is normally destroyed within a second or so. So it's very fortunate that I had a current limit set on the power supply I was using. Because the output voltages of this converter circuit are present on the edge connector at the rear of the spectrum, then it's quite common for them to be briefly short-circuited if something is plugged in or removed while the power is turned on. And through the mechanism I've just described, that frequently causes TR4 to be destroyed, and this is a very common cause of dead ZX spectrums. I want to try to prove my suspicion that the problem is due to one of the voltage converter circuit's outputs being overloaded and not something overloading the main 5V power supply line, other of course than the voltage converter circuit itself. So I've connected this test clip here to short together the base and the emitter of transistor TR5. In that situation, the base will be held at 5V, hopefully, which will ensure that the transistor stays turned off. That means there'll be nothing to drive the base of TR4, and so it also will stay switched off, and no current will be able to flow through it, which is what I think was causing the overload condition before. I've connected the oscilloscope probe back to the collector of TR5, so I'll be able to monitor the voltage there, and it should stay close to 0V. And this multimeter is connected to the 5V power supply line. It's not normally a good idea to carry out this test, because if the lower RAM ICs are powered without all of their power supply voltages, they tend to fail. But I strongly suspect at least one of them has already done that, and that's even more likely given that we know the voltage converter circuit has been extensively messed about with in the past. So I will briefly connect the 9V power supply to this spectrum. And disconnect it. The power supply showed that the spectrum was drawing a current of just over 400 milliamps. We could see that the 5V power supply rail was at more or less 5V as expected, and on the oscilloscope TR5's collector stayed at about 0V, so I think that's proved the point. The only things connected to the output of the voltage converter circuit are the lower RAM ICs and IC14, the video chroma generator. That's generally very reliable and hardly ever causes this type of problem, so for now I'm going to have to assume that one or more of the lower RAM ICs is faulty, so I think the next step will be to remove those. As hopefully you can see, I've now removed all 8 of the lower RAM ICs, and I've connected the spectrum up again exactly as I had the first time when I tried turning it on. So let's try again. Power supply says it's drawing 490 milliamps, so the current limit isn't operating this time. Let's check the power supply voltages on the circuit board. This is 5V, that's fine. Opposite should be 12V. And in the top left, minus 5V. The picture on television is exactly what I'd expect for a spectrum with no lower RAM installed. And here's what the oscilloscope shows. The blue line marks the 0V point. So it seems certainly it was the case that one or more of the lower RAM ICs was faulty, and I think it most likely this spectrum will work properly if it has some working lower RAM installed. So on that note, I think I will go ahead and install one of these lower RAM replacement modules. Quite often I install sockets in place of the lower RAM and fix the module into those. However, this time I've soldered it directly to the Spectrum circuit board. That should make for a more reliable connection, and even if it should be desired to remove it in the future, it shouldn't be too difficult, as it only has 20 connection points as opposed to the 8x16 of the original 4116s. It would even be possible to replace its surface mount components without removing the module if that should ever be necessary. So let's connect it up again and see whether it works. It certainly looks as if it's working now, and I'm not too surprised about that given the steps to diagnose the problem that have taken so far. By the length of time it took for the system to initialize, I think it's working as a 48K spectrum. If I use a small screwdriver blade to briefly short the leads of capacitor C27, it forces the spectrum to reset, and certainly it took longer than it would for a 16K spectrum, so that means the ROM's RAM test routine found more than 16K of working RAM. Let me plug in a keyboard membrane. See whether I can enter some commands. Of course, it's a bit tricky typing just by pressing on the membrane rather than having a proper keyboard. I'm going to try to display the value of the system variable PRAMT that shows the address of the highest working byte of RAM that the ROM's RAM test routine discovered. That's very good. Both bytes are 255. That's both bytes of this 2-byte system variable. So that means that all 48K of the spectrum's RAM were detected as correctly working by the RAM test routine. That's not a guarantee it's working properly, as it's only a very simple test, but it's an extremely good sign. Let's try one more command. And that shows that the colour video circuitry, etc. is working well too. Here it is back in its lower case half. I've done a bit of general cleaning. I've reinstalled the heatsink with a smear of thermal grease between it and the voltage regulator, and reattached the reset switch, which I found to be working properly. And there's a convenient hole in the upper case for it to be mounted in. There isn't a keyboard membrane. The owner apparently has one ready to fit, so I will temporarily install my own so I can carry out some further tests. I'll also do the owner a favour and remove the residue of the double-sided tape from the rear of the keyboard faceplate and from the sides of the case, so it'll be ready to easily install the new membrane and stick this back down again with some fresh tape. The Spectrum's been on for a few hours now. For most of that time it was running a RAM test program that reported no errors. I've also checked loading and saving using a cassette recorder and verified the correct signal is present on the CPU's M1 output line. It's quite common to find CPUs where that is faulty, and this signal is necessary for correct operation of some add-ons such as the SpectraNet interface. As I'm sure you can see, I've just loaded Manic Miner, and I think I can conclude that this Spectrum's now working perfectly.